Okay, so we're very pleased today to have Andrew Wetzel join us from UC Davis. He did his PhD in Berkeley, then did postdocs in Yale and at Caltech Carnegie. He has been faculty at UC Davis since 2017. He is an expert in simulations, has done many simulations and derived many interesting results from them. And today he's going to tell us about a particular set of simulations looking at the Milky Way. Okay.
Thank you, Will. Can everyone hear me okay?
Yep.
Okay, now let me go ahead and reshare my screen.
Yep, all looking good.
Fantastic. So let me make sure I get this perfect. Well, thanks for inviting me to give this virtual seminar. I believe I visited in person to give a seminar about 5 years ago, and it's a pleasure to be back in a virtual sense. Although, you know, as much as I would have liked to leave California and visit you guys at Waterloo in February, this will have to. So I think when I gave a talk 5 years ago, we were just finishing the first version of our new generation of Milky Way-like simulations, and I talked a lot about our first results analyzing the dwarf galaxy populations of the Milky Ways in these types of simulations. Since then, there has been, I think it's fair to say, a revolution in Milky Way science. There's tremendous advances in our ability to measure populations across the Milky Way. So today, instead, my talk will focus on how we're using these simulations to understand the Milky Way galaxy itself. And so just to give sort of a visual impression of where we are, one of the images you're staring at here is the actual Milky Way we live in, and one of these is a virtual Milky Way that we don't live in. Most of you can probably guess which is which, but just to give you a visual sense of sort of where we're at today in terms of the ability to simulate a galaxy that does in fact resemble our Milky Way galaxy. So there's a lot I could say in an introduction about all of the advances in the last several years of our ability to measure the Milky Way. I think I'll sort of summarize it with sort of the pithiest thing I could say, which is that thanks in part to the Gaia Space Telescope and now also to a multitude of ground-based spectroscopic surveys, we've essentially moved from being able to just take a picture of our Milky Way galaxy to instead now, as this movie will hopefully show, we can basically create a movie of our Milky Way, right? So what you're seeing here is the proper motions, across the sky motions of stars as measured from the Gaia Space Telescope. So Gaia is basically an astrometry machine, providing precise astrometric positions, parallax distances, and as you're seeing here, across the sky, proper motion measurements, in addition to a component measuring radial velocities through spectra. And this together is providing up to 6D phase space coordinate positions for, I think currently Gaia has measured at least some information for some 2 billion stars in the Milky Way. So as I said, Gaia is basically an astrometry machine. And then in parallel, there's quite a number of efforts now. And this compilation from Bruno Kohlmeier's 2017 paper is now out of date in the sense it's missing several, but it just gives a sense of the multitude of complementary ground-based spectroscopic surveys that are essentially measuring spectra to provide both radial velocity, but in even more detail, measuring dozens of elemental abundances per star. And so you can get a sense here, we're talking on the order of tens of millions up to about 100 million stars that soon will have measured elemental abundances across the Milky Way. And currently, sort of the current state of these sorts of surveys, on the left here, for example, just shows the footprint of the recent data release from the Sloan Apogee survey. Most of these spectroscopic surveys are measuring stellar populations relatively close to the sun, so within a few kiloparsecs of us. So we're getting a somewhat limited view of the Milky Way. But for example, future surveys like Sloan 5, the plan is essentially to measure stellar populations across the entire disk, as you can see on the right here. And so this is basically what has been happening and what will continue to happen over the next few years in terms of Milky Way science. So just sort of summarize that Thanks to Gaia in particular, we're now able to measure up to 66 dimensions of orbital phase space coordinates for up to 2 billion stars currently across the Milky Way. And thanks to ground-based spectroscopic surveys, we're also getting dozens, in some cases, 50, 60, 70 elemental abundances per star. And in combination with that, what's really an emerging field is the ability to improve our measurements of the ages of stars, right? So in addition to sort of the traditional isochrone method of fitting ages of stellar populations, there have been some pretty impressive advances in the last few years on methods like astroseismology to look at the seismic activity, the photometric pulsations of stars, and use that as an age calibrator. Other methods as well, like gynochronology, to look at the spin down of stars and use that as an age date. So together, these are providing significant improvements in our ability to measure the ages of stars. So you can sort of get a sense here. We're measuring, in some cases, complete phase space information. We're measuring dozens of elemental abundances, and we're measuring ages of stars. So this is an exquisite data set to really dissect various facets of how our Milky Way formed, what it's made of, and what the distribution of mass is around us. So just to kind of summarize some big picture goals of what we in principle can do with this current data set. So to just sort of introduce, of course, the necessary buzzwords that we use so that we can propose and get funding for this sorts of science. Every subfield needs its buzzwords. So in this one, a common one we describe as near field cosmology. And for the purposes of this talk, I think the way I would define near field cosmology is a goal to measure the distribution of dark matter around us in the Milky Way, at least the spatial distribution, and in some cases, perhaps get influence on the velocity distribution of dark matter as well. This is near the sun, this is throughout the halo, and then nearby dwarf galaxies. With the ultimate goal, of course, is we want to test and constrain models of dark matter by doing this. Another buzzword, of course, is galactic archaeology. The idea here is we're measuring precise, we're making precise measurements of the Milky Way today, and use that to basically infer the full formation history of our galaxy, to basically reconstruct our full cosmological formation history, not just recent history, but full cosmological formation history. And one of the key goals here would be to understand what created our Milky Way, the building blocks. And I sort of think about the building blocks in two ways, one of which is the ex situ building blocks, which is the galaxy mergers that built the Milky Way over time. And then also the internal building blocks, things like star clusters that we think mostly created the population in the disk. And then closely related to galactic archaeology, I sort of describe separately here, which is galactic metal enrichment, right? So again, motivated by our ability to measure dozens of elemental abundances for up to 100 million stars across the Milky Way, we can really understand in detail the metal enrichment of our galaxy, since metal enrichment is a very fundamental aspect of how galaxies form over time. And I think what, in principle, is quite exciting is to actually take this question in reverse and ask, when we're measuring dozens of elemental abundances for 100 million stars, this is an exquisite data set to basically measure elemental abundance patterns in stellar populations across the Milky Way. And this should provide an exquisite constraint on underlying models of stellar nucleosynthesis. And I think this will be one of the most, in my opinion, this may be one of the most interesting things to emerge from these spectroscopic surveys, is really putting tight empirical constraints on fundamental nucleosynthesis models, which, for those of you who worked on this, there's still tremendous uncertainties in, for example, how much nitrogen is produced by core collapse supernova, or the exact ratio of our process elements like gold produced from neutron star mergers versus core collapse supernova. So questions like this, the elemental abundance patterns in the Milky Way should provide strong empirical constraints to understand this. And I'm just going to stop right here because I forgot to say in my intro talk, I welcome anyone to interrupt my talk with questions. Please just unmute yourself and speak up. I encourage you to do so. Okay, so thanks largely to Gaia and these new generation of spectroscopic surveys, we're now in an era of precision measurements of the Milky Way. And maybe it's a bit too strong to think about to even mention precision galaxy formation, but at least we can use that as a guiding principle motivated by the tremendous advances in precision cosmology over the last few decades. So we have precision measurements of the Milky Way today, and the question is, how do we use those precision measurements to understand how the Milky Way formed? But the key challenge here is we really want to understand Milky Way formation, not just in its recent history, although that's interesting too, but its full formation history across nearly 14 billion years of the universe evolution. That's where it's much more challenging. Now, what's kind of interesting, so we have very firm measurements of the Milky Way today. We also have very firm measurements of the initial conditions of the universe, thanks, for example, to measurements of the cosmic microwave background. So we have precise initial conditions and precise measurements of the final conditions, at least of our own Milky Way. So the challenge is, how do we connect the dots? How do we connect our understanding of the early universe to what we can understand how the Milky Way formed from those initial density perturbations? So of course, it's quite challenging just to directly connect these dots, right? We're going from small density fluctuations, linear perturbation theory to describe the early universe, to a highly nonlinear system with complex baryonic processes, right? So we can't exactly connect the dots in such a straight line. So we are really building here on the last decades of advances in modeling how structure forms in the universe. So starting, for example, with the cosmic microwave background, the next step is our ability to model large-scale structure, so through large dark matter-only simulations, or in some cases, baryonic simulations that simulate the large-scale structure of the universe. And then in the last 2 decades or so, there have been tremendous advances in techniques to zoom in on a patch of this large-scale structure. And for example, zoom in on a region that we think would form a Milky Way mass halo, and we're able to simulate that at exquisitely high resolution to resolve all the small-scale structure in the dark sector. And in the last 10 to 15 years, there have been tremendous advances on adding on top of that methods of hydrodynamics to model the gas physics of how gas accretes into a halo and collapses to the center to form a galaxy. And of course, there also advances in ability to model how stars form and the feedback processes from stars. So I'm showing you at the bottom here is a fly through one of the Milky Way mass simulations I'll discuss more in my talk. And then finally, what I'll mention at the very end is then we can take the last step of creating synthetic Gaia-like observations within these simulations. And then finally, we're in a position to do an apples-to-apples comparison to what we measure in the Milky Way today. That's all predicated on our understanding of the early universe. So it's through these cosmological zoom-in simulations where we add the baryonic physics that we can connect the early universe to precise measurements of the Milky Way that astronomers are measuring today. So that brings me to the overview of my talk today. So the first part of my talk, I'll just describe the current status of our FIRE cosmological zoom-in simulations, in particular our simulations of Milky Way and local group-like galaxies. And then I'll discuss a little bit of some insights that we've gotten from these simulations to understand the formation history of our Milky Way galaxy. Then I'll discuss some ongoing work to understand how to use elemental abundance patterns in the Milky Way to understand its formation history and to really guide this idea of chemical tagging, of using elemental abundances of stars to map the formation history of the Milky Way. And then finally, I'll discuss some sort of recent work of zooming in on the small scales and our ability within these simulations to resolve small scale features like giant molecular clouds and star clusters. So just to highlight my current and former members of my group at Davis, whose work I'll highlight a little bit today. Most of the work I'll describe today is coming from 2 of my PhD students, Isaiah Santisteban and Matt Bellardini, but I'll also highlight at the end of my talk some very nice works for 2 former postdocs in my group, Samantha Benincasa, who's now a postdoctoral fellow at the Ohio State University, and Sarah Loebman, who was a Hubble Fellow here at Davis and has now recently started a faculty position at University of California at Merced. So very quick overview of these simulations. And again, if you guys have any questions, please just interrupt. I'm happy to elaborate on anything. So the simulations I'll show you are all part of the feedback and realistic environments collaboration. So our goal with these simulations is to model as best we can dense multi-phase interstellar medium and using the zoom in technique to achieve this at high resolution. So we can actually resolve relevant features in interstellar medium in a fully cosmological setting. So the goal is to push on resolution as much as we can. So most of the simulations I'll show you today are at a few thousand solar mass resolution. But in fact, we've recently finished resimulating some of these galaxies all the way down to a few hundred solar mass resolution. And in terms of spatial resolution, we're typically achieving scales here of a few parsecs. Again, the goal here is to resolve features like molecular clouds and at least massive star clusters, the building blocks of the disk of the Milky Way. And these simulations include a full suite of baryonic physics, including gas coolings from atoms and molecules and metals down to cold temperatures, 10 Kelvin. And one of the, we think, really important features here is the modeling of star formation. And in particular, modeling star formation is occurring in self-gravitating molecular clouds, where the density threshold for star formation in these simulations is quite high. So again, we're getting clustered star formation in dense clouds as we observe it to occur in the Milky Way. So sort of the history of this field is a bit checkered. Sort of in the bad old days when simulations were relatively modest resolution, achieving like kiloparsec scale resolution, it was very difficult to take fundamental models of star formation, stellar evolution, things like star clusters and stellar populations, and implement them when you're at sort of kiloparsec scale resolution. So in the bad old days, the approach was to sort of coarse grain your model, but it was a little unclear how to do that. And then you basically had to run the simulation multiple times and tune the parameters until you got a kind of galaxy that you liked, that it looked like real galaxy populations. And what our goal has been in FIRE, and I think we've showed there's at least some promise here, is if we can push to high resolution thanks to using zoom-in simulations, and we can resolve salient features of the interstellar medium and spatially resolve relevant scales of star forming regions, that allows us to take a more forward modeling approach where we can simply implement standard stellar evolution models, think Starburst 99, for example, and put them in a very vanilla sense and see what kind of galaxies come out. So that's been the at least principle we've been using in developing these various generations of FIRE models. And so the idea is if we could push to high resolution, then we can directly implement standard stellar evolution models. Of course, stellar evolution is itself a very unsolved problem, a lot of interesting questions. So there's still a lot of uncertainty there, but at least the models we put in here are tethered to those standard stellar evolution models that are coming out of the stellar evolution community. And another thing we think is really important is explicitly modeling the different channels of stellar feedback, the different ways that stars affect their surrounding interstellar medium. So the three sort of classes of feedback channels we're modeling in these simulations, the probably most important of which is supernova. So that includes both core collapse and type 1a supernova. We're modeling the radiation from stars. So this includes radiation pressure from scattering off of the interstellar medium. This includes photoionization heating, the generation of H2 regions, photoelectric heating by interactions with dust, and then finally stellar winds. So stars, in particular massive stars, shed lots of mass and lots of momentum through stellar winds. And then late stage stellar evolution like AGB stars also could drive significant stellar winds. And so the idea, if you look at this image on the right here, so here's a star forming region 30 Doradus, you can see a young star cluster here that even within a few million years of its formation has already evacuated a cavity in its host molecular cloud, right? So you can see stellar feedback in action here. And then this propagates all the way up to galactic scales. For example, everyone's favorite example of a starburst, M82, where you can see that sort of edge-on disk galaxy here, and it's driving winds above and below it, as you're seeing in red there. So maybe I'll just pause here for a moment in case there are any questions about the simulation methods after this very quick overview.
Does I assume the time steps in the simulation line up so that you're resolving relevant stellar time scales for O and B stars?
Yeah, so the time stepping in the simulation is adaptive. It's adaptive both to the local gravitational acceleration field and for star particles, for example, it adapts according to the underlying stellar evolution model. So it takes very short time steps for when the stellar particles are young, because of course, stellar winds and supernova are occurring on very short time scales. So, so just to give you an example, I was very excited when I finished the first of these simulations and I looked at the time step history of the simulation. And I think the shortest time step it took was about 30 years, which, it was younger than me. So I felt proud that it took a time step that was less than the time step I've taken in life. So that's a very important part, we think here, of not just spatially resolving, but time resolving all of these processes.
Right. Good. Thanks.
So I had a question about the modeling as well, and that is the role of spiral arms, both collecting the material together or shocks that start the star formation process. Is that in there in any way?
Yeah, so that's not put in, of course. So I'll show you some movies, but we start with cosmological conditions that collapse and form a galaxy. So spiral arm patterns phenomenologically emerge from these simulations, and they're certainly there. And maybe you'll be able to see that in just a moment.
So going back to Mike's question, so what is your spatial resolution or the highest spatial resolution that you get?
So the spatial resolution is adaptive in the gas, that adapts down to 1 parsec, and in the stars, it's 4 parsec for these simulations.
I see, 1 parsec and 4 parsec. And why those numbers? I mean, is there?
Yeah, adapting down to 1 part. So again, the gas resolution is fully adaptive. It adapts to the local, basically density kernel according to how many neighbors are around it. We've just set 1 parsec as a floor, as a minimum, just to prevent some numerical issues of letting it get arbitrarily small. So that's where that comes from. Typical gas cell has in the ISM would have a resolution of a few tens of parsecs, but 1 parsec is the highest it gets. And the choice of 4 parsecs for the stars is motivated by our density threshold for star formation. So we have a star formation density threshold of 1,000 particles per cubic centimeter. And if you ask what that translates to in terms of mean interparticle spacing at our resolution, that's about 4 parsecs. So that when we form a star cluster of particles, they're actually self-gravitating at the density they're forming at.
Okay, thanks.
Okay, so here is finally a movie of this now. Let me just say what you're going to see and then I'll play it. On the left is a real color visualization of the stars forming from this region. And on the right is a visualization of the gas in this region, color-coded by temperature. So these are zoom-in simulations. So you're just seeing kind of an irregular patch here, but this is embedded within a large cosmological volume with dark matter particles surrounding it, which you're not seeing. And on the right, you're going to see the gas that's initially expanding with the expansion of the universe, and it will collapse under its own self-gravity. And then on the left, you'll see the stars forming out of the gas on the right. So in the initial conditions, this proto Milky Way system was a bunch of small galaxies, all in the process of merging together. And on the right, you can see the gas collapse through these filamentary inflows. And you can also see how the galactic winds being driven off of these galaxies through the various stellar feedback channels are blowing gas out of the galaxy and heating the gas around the galaxy. And note the scale here is a few hundred kiloparsecs. So you're going to see basically the entire Milky Way system, including the stellar halo and the dwarf galaxies forming on the left.
Was the large scale environment like chosen to mimic, the local group's large scale environment? Or
that's my next slide. Yeah, that's my next slide. Yeah. So let me just cut ahead since this movie is not super interesting anymore. So we have sort of 2 subsuites here specifically to address Neil's question. So what I'll show you today, we have 8 cosmologically isolated Milky Way mass systems. So the idea is we zoom in on just a single Milky Way mass halo. And that's purely chosen for computational reasons. It's more expensive to simulate a denser region. There's no physical motivation here. It's purely computational. It's cheaper to simulate a Milky Way that doesn't have a massive system around it. However, we don't find ourselves living in such an environment. We find ourselves living in a local group with a Milky Way and M31-like pair. So we've also have a separate suite that's built on Shea Garrison Kimmel's previous Elvis suite, where we have 3 local group-like pairs of Milky Way plus M31 halos at about the same separation as the Milky Way and M31. And I'll try to highlight, at least in some cases, where we think that matters. We have not done, however, what some other groups have done, which is additionally try to constrain the sort of local 10 megaparsec environment around the local group. So there's no constraint on the larger scale environment than that. And here is just an image of what the variety of disky Milky Way mass for morphologies we get at redshift 0. So some of these things you'll see look pretty disky, but of course there's a range of morphologies depending on the detailed formation history. And I think somebody asked about like spiral arm structure. So you can see, especially in some of the systems on the right there, you can see some nice spiral arm-like patterns in the stellar populations. Okay, so that's a quick introduction to the simulations themselves. So then I'd like to move on to some insights where we've used these simulations to understand the formation history of our Milky Way galaxies. This is work led by my PhD student, Isaiah Santisteban. So some very basic questions you might want to ask about even how to think about Milky Way formation history is, when did the Milky Way form? And what exactly do you mean by Milky Way form, right? There's a lot of different definitions here. So one question we wanted to address, which is especially if we're trying to use the stellar record today to understand the formation history of the Milky Way going back almost 14 billion years, is when did a single Milky Way emerge from that sea of dwarf galaxies you saw at the start of my movie? When does it even make sense to talk about there was a main Milky Way progenitor as opposed to just a bunch of Milky Way progenitors? And related to that is, what were the actual mergers, the ex situ building blocks that built a typical Milky Way mass galaxy across cosmic time? So again, I'll just show you the first part of a movie I showed you before. So this is what the simulation looks like in the first few billion years, and I'm going to pause it here right at redshift 2.8, which is about 11.5 billion years ago. And so I challenge you to point me to where the main Milky Way progenitor is in this movie. Again, this will form a single Milky Way-like galaxy at the end of the day, but it's kind of visually apparent here that there is at least some time threshold going back where it doesn't even make sense to even talk about, conceptualize a single Milky Way progenitor. So I think it's important that we sort of understand when is that, because it informs the way we think about old metal poor stellar populations in the Milky Way today. So again, one of the real uses of these simulations is we know they form Milky Way-like galaxies at redshift 0, and so we can go back and look across time at connecting the dots to what was going on at arbitrarily high redshift. All right, so first of all, we can look at what was the building blocks of a Milky Way in these simulations. So this plot here shows on the y-axis what's the number of galaxies that built the entire Milky Way system in these simulations as a function of redshift. So basically, if you added all the dwarf galaxies that ever merge in, some of which survive, most of which don't, what were the number of galaxies as a function of redshift? And so it looks something like this. So you can see, for example, if we look at massive progenitors, some progenitors with stellar mass 10 to the 9, like LMC mass galaxies, typically maybe one or two of them went into forming a Milky Way, and it tends to have fallen into the Milky Way halo relatively recently. And you can basically see hierarchical structure formation at play here. As we go down in mass, the numbers of progenitor galaxies peaks at higher and higher redshift, such that we can resolve dwarf galaxies down to stellar masses of about 10 to the 5 in these simulations. And we find that of the order of about 100 of them typically went into forming a Milky Way mass system. Of course, most of them don't survive. We only observe about 12 of them around the Milky Way today. So most of these 100 or so dwarf galaxies merged in, and they formed the Milky Way and its stellar halo. But one thing you have to be careful about is, yes, a large number of dwarf galaxies went into forming the Milky Way, but if you weight them by their stellar mass, because of the steepness of the stellar mass function, most of the ex situ mass that merged into the Milky Way didn't come from those 100 faint dwarf galaxies. Most of the mass that merged into the Milky Way came from the 1 or 2 or 3 most massive mergers. So this just shows the cumulative amount of ex situ mass that was deposited by different mass galaxies at different redshifts. And you can see it basically, the story is the same at all redshifts, that the vast majority of the ex situ mass was deposited by the few most massive mergers. So that'll be an important point that will relate to what I'll talk about in a little bit. All right, so what's really striking about the advances in the last few years of galactic archaeology of the Milky Way is, thanks to the variety of surveys, we now think we have a nearly complete census by mass, and I'll emphasize that by mass, of the Milky Way stellar halo, of the galaxies that merge to form the stellar halo of the Milky Way. So here's a plot from Naidu et al. From the H3 survey, which is the relative fraction of stars in the stellar halo, and then as a function of galactocentric distance, that measurements are able to date came from various mergers, right? So if we're close to the disk, we have basically the thick disk component of the Milky Way and probably a component of in situ stars that got puffed up and formed the inner halo. One of the, probably the most massive, significant merger event, this so-called Gaia, Sausage, Enceladus, I like to call it the enchilada, it's sort of a moral average between those, deposited most of the stars in the stellar halo. Of course, Sagittarius is still phase coherent, it's still a stream around today, but now this handful of lower mass progenitors, Aleph and Thamnos and Wook, we basically have accounted for, we think, something like 90% of the, by mass, of the objects that form the stellar halo. So there's really only 10% left to account for, but of course that last 10% would have been probably those hundreds of lower mass merger events. But by mass, we've basically, the story is almost here of what objects built the stellar halo of the Milky Way. So it's really a remarkable statement how far this field has come in just a few years now. Okay, so coming back to now the results from the simulation. So now, having described the building blocks of the Milky Way galaxies in these simulations, Isaiah next looked at this question of when does it make sense to call a Milky Way progenitor as having formed? And our view on this is that probably the best way to define a single main progenitor is when did the relative fraction of stars being formed transition from being formed in ex situ in a large number of external galaxies that will merge in, versus when did most of the stars in the proto Milky Way form in a single main progenitor. And so this shows that fraction. So what fraction of stars formed in a single main progenitor as a function of redshift? There's lots of lines here, don't worry about them. First of all, just look at this median curve here, which is across our 12 or 14 galaxies that went into this analysis. So on average, the median transition epoch is about redshift 3.5. So across our suite, before redshift 3.5, most stars did not form in a single main progenitor. So I don't think that makes sense to talk about the main progenitor. But after redshift 3.5, I think it becomes quite sensible. But now I also want you to look at when we separate these formation histories by environment now, and I think this is the most important difference we've seen across all the different things we've looked at in local, whether it matters, whether we're simulating local groups versus isolated Milky Ways. The most important difference we found is this one, which is that the host galaxies in local group environments form earlier. So the galaxies in local groups transition to primarily in situ star formation significantly earlier than our simulations of relatively isolated Milky Ways. And it's simply because the galaxies forming in halos in local group environments form stars in their main progenitor sooner than galaxies forming in isolated halos. And this seems to be simply a reflection of the collapse history of the dark matter halos they're forming in. So it turns out that you can look in dark matter only simulations, halos in local group environments collapse earlier on average than halos in isolated environments, because halos in local group environments are forming by definition in a denser patch of the universe. And this seems to reflect itself in the formation of stars in the main galaxy in our simulations as well.
So just to clarify, in situ means formed in the main progenitor, and the main progenitor means the most massive one, I guess.
Yeah, that's right. Yeah. So I think this is one area where it probably does matter from galactic archaeology point of view that we live in a local group, at least from our simulation so far, limited statistics, but it does seem like that would lead us to believe that the Milky Way and M31 would have formed their stars in their main progenitors sooner than a typical Milky Way mass galaxy in the universe. Okay, so I'll move on to a slightly related question, but Isaiah's second paper, which then was targeted to understanding the very old stellar populations in the Milky Way. And it was motivated by a very interesting observation to emerge from the Pristine survey. So the Pristine survey is measuring metal poor populations across the Milky Way. And in a series of papers, Sestito et al. Pointed out a curious feature, which is that amongst very metal poor stars, so metallicities less than -2 all the way down to -4, is if you look at the dynamics of metal poor stars in and around the Milky Way, is metal poor stars strongly prefer prograde disk orbits. So it's about a factor of 2 to 1 preference, you can see here, of metal poor stars basically orbiting along with the disk in a disk-like configuration, as opposed to orbiting retrograde to the disk. So metal poor stars are on, basically to arbitrarily low metallicities, are on disky orbits. So that's kind of curious from sort of the standard hierarchical perspective. So, you know, going all the way back to say Searle and Zinn, where the idea is that the early ancient metal poor population of the Milky Way formed through mergers of a variety of low mass dwarf galaxies. You would think if, as I showed from the simulation, something like 100 dwarf galaxies went into forming the early stellar population of the Milky Way, why should they all fall in such an aligned way to exhibit such strong coherence with the orbit of the disk today, right? There's no particular reason to expect that. But remember, you have to be careful. While it's certainly true, at least in our simulations, that hundreds of low mass dwarf galaxies went into forming the early stellar population of the Milky Way. Remember that by mass, that's not necessarily true. By mass, most of the mass of the Milky Way, the accreted mass of the Milky Way, is coming from a few most major mergers. So first of all, Isaiah looked into this prograde bias of metal poor stars in our simulation. So we just select metal poor stars with iron abundance, in this case, less than -3.5, I think. And then we just look at the ratio of such metal poor stars that are on prograde versus retrograde disk orbits. Sorry, this is now as a function of iron abundance, of metallicity. And the X's here show the observed values for the Milky Way. And the thick line shows the median amongst our suite. And you can see the different simulations shown individually there. And I was actually pretty shocked when Isaiah made this plot, and then our median line sat almost right on top of the Milky Way observations with a prograde bias of about 2 to 1 on average, although some hosts are much higher, some are lower. So our simulations basically bear this out as well, that 11 to 12 of our simulations have this very strong bias of metal poor stars to arbitrarily low metallicity wanting to be on disk-like orbits today. So what's going on here? What causes this? Did all those, dwarf galaxies merging in somehow know to be aligned? So then Isaiah basically looked at the history of this prograde bias. So we can look in one of our simulations as a function of look back time, what was the prograde bias of metal poor stars? So at redshift 0 up here, it's close to 2 to 1, maybe 1.5 to 1. And that was true for many gig years in the past. But there was sort of this transition about 8 gig years ago where it went from having no prograde bias to having a strong prograde bias. Okay, and then this arrow, as you might have guessed by now, shows when the most major merger happened in the history of this galaxy. And then in the bottom panel, we can look at the relative angle between the orbit that this galaxy merged in on and the orientation of the disk of the main progenitor. So the angle between the orbit of the satellite and the Milky Way-like disk. And we find that before this merger event, there was basically no alignment. And in fact, it was quite noisy because there wasn't even necessarily a well-defined disk in this progenitor Milky Way. And then after this merger event, boom, you see this basically went into alignment. And then afterwards, it was a relatively long-lived, regularly oriented disk direction. So what we find in most of our simulations is the following scenario, that a major merger, typically a mass, the LMC or the SMC, deposits the majority of the metal poor stars. So of course, most of the stars in such a galaxy aren't metal poor, ultra metal poor. There may be -1, but not -3 or -4. But if you think about it, even if just like 1% of the stars in the LMC are ultra metal poor, so the LMC is stellar mass 10 to the 9, 1% of that is 10 to the 7. So that already is far more stars than in all of the ultra faint dwarf galaxies of the Milky Way combined. So a single massive merger, even if there's just a tail to ultra low metal stars, that can easily overwhelm the entire population of ultra metal poor stars that end up in the Milky Way. So that merger deposits most metal poor stars. And what we also find is that since these mergers happening at high redshifts, they tend to be pretty gas rich. So these gas rich mergers also are really good at helping to seed the disk of these Milky Way simulations. So before this, there wasn't necessarily a well-defined disk, or it was wobbling around because of rapid accretion events. But after this major merger deposits a lot of gas on a relatively coherent angular momentum vector that settles in and basically determines the eventual orientation of the disk that emerges. So it's not a coincidence, therefore, that metal poor stars are on disk orbits today, because the same event that deposited the metal poor stars also told the disk what direction to form. And we find that this is a pretty typical scenario. Go ahead, Neil.
So following that major merger, I think the NIST data seems to like slowly process, I guess, over time. Yep. What's causing that? Like, do you know?
Yeah, we didn't look into that. There's a variety of precessions we see. So it probably has to do with, there's still additional accretion, both from cold mode accretion, but also hot accretion from cooling flows that can gradually torque the disk here. So probably something like that. There's also some minor mergers that continue. We didn't dissect that in detail, but it's an interesting question to follow up on, is sort of how much precession typically happens.
Okay, all right, thanks.
But certainly, these disks aren't fixed in orientation for all time. These disks are, for the most part, precessing. I just show you one example here. Okay, so just to summarize that part of my talk, sort of insights we think we've learned from these simulations is we have to be a little bit careful of even how we think about galactic archaeology. It probably doesn't make sense to talk about a single main progenitor of the Milky Way until about 12 gig years ago. Before this, there really is no meaningful sense of a main progenitor galaxy. The most important difference we see of local group-like systems versus isolated Milky Ways is that the Milky Way mass galaxies in local group-like environments form earlier. They form their stars earlier in the main progenitor. So they're less driven by ex situ star formation at this early epoch. And if you want to sort of remember, a good number to remember is something like 100 dwarf galaxies of stellar mass 10 to the 5 went into building a typical Milky Way. But don't forget, because of the mass function, most of the mass is weighted to the 1 to 2 most massive major mergers. And because of that, that helps explain, to the extent that these mergers are also gas rich, why most metal poor stars in the Milky Way today are on prograde disk orbits, because the same 1 to 2 major mergers that deposited most of the metal poor stars also determine the eventual orientation of the disk of the Milky Way. Okay, so I think I'm running a little long the time, so I'll just do the second section and end there, because I also want to highlight nice work from my other student, Matt Bellardini, on chemical tagging. So one of the techniques that has developed in the last, I guess, 2 decades now, in terms of an approach to this whole idea of galactic archaeology is chemical tagging. So our ultimate goal here is we want to reconstruct the full formation history of the Milky Way. Here's a problem. We can measure 60 orbital phase space of stars today, but nobody said that those were conserved across the formation history. In fact, in general, they won't be, right? So events like mergers, dynamical heating, scattering off of molecular clouds, spiral arms, radial migration, these will all change the orbits of stars on cosmological timescales. So, orbits today are useful to model the mass distribution and look at the instantaneous dynamics of the Milky Way, but using them as a record of the formation history of the Milky Way can be challenging for this reason. So what we really want is some sort of orbital invariant tag so that we can look at a star and know that this property of the star did not change between the time it formed and today, so that we can use that to basically reconstruct populations of stars and reconstruct regions of the formation of the disk across cosmic time. So the easiest one to measure is simply elemental abundances. We don't think the surface elemental abundances of stars are changing in any meaningful level over the the typical ages of stars. We can measure them. So therefore, the chemistry, the elemental abundances of stars provides this orbital invariant tag, so we can tag stars by their elemental abundances, chemical tagging. And if we can then model the elemental abundance distribution of stars as they formed across the Milky Way, we can use that to understand where they came from. I'll also add, just in passing, in principle, stellar age also provides a record of when the star formed, and you can use that as a tag. And again, there have been tremendous advances there, but currently it's much easier to measure precise elemental abundances than it is to measure precise ages for large numbers of stars. So still, I think for the foreseeable future, the easiest approach here will be in the abundances. Okay, so you can sort of think of two regimes of people trying to use chemical tagging for these observations. There's sort of a fine-grained or strong chemical tagging, where, for example, we want to identify stars that may be distinct throughout the disk today, but that were born in the same star cluster. So here we're thinking about small-scale chemical tagging and largely chemical tagging of stars that formed reasonably recently, so they're not so phase mixed across the disk. And there's been lots of work on this in the last few years, really exciting. There's also so-called weak or coarse-grained chemical tagging, where instead of trying to find stars born in the same cluster, we're just trying to identify stars born in the same patch of the disk. So say at small radii versus large radii in the disk across cosmic time, or in situ stars versus ex situ stars. And what I'm about to describe to you is focused mostly on the weak or coarse-grained chemical tagging approach. So you can think about two regimes of chemical tagging as sort of limiting cases to wrap your head around it. So in the extreme model, where the ISM of the Milky Way is completely mixed and uniform at any time. So at early time, every part of the disk has the same elemental abundance of newly formed stars. And at late time, the metallicity is increased because of overall metallicity evolution, but the spatial information the spatial distribution is uniform. So this is a case where there is no basically use of chemical tagging. The abundances you measure of stars don't tell you anything about where they formed in the disk. So it's not very useful, although it is very easy to model. To contrast with the other extreme regime you might think about, where every star cluster has a distinct elemental abundance pattern that is different from every other star cluster. So tons of information content for chemical tagging. But this would be very challenging to model, right? And of course, reality is going to sit somewhere between these. So there's sort of a trade-off between how much information content there is of chemical tagging and how difficult it's going to be to model the full three-dimensional variations across the disk, across time. So the goal of Matt's work is to use these simulations to simply understand in a fully cosmological framework with complex mergers and non-equilibrium dynamics and spiral arm patterns that introduce complex spatial variations to the abundances, what were the initial conditions of elemental abundances across the disk of the Milky Way across its formation history? So we'll just tag stars right when they form and look at patterns of the abundances in those stars. So when we want to look at the there's sort of four parameters here. So where Z is, say, the elemental abundance of element I, we want to know how did that abundance change across time? How did it change across the radius of the galaxy? How might it have varied as a mutual position within the galaxy? And then finally, the vertical position within the galaxy. So this is the 3D plus 1D space, 1D time dependence of elemental abundances in these disks.
Do you, just a quick question, do you include the differences in Wolf-Rayet stars between the N types and others? Because some are very nitrogen abundant, some are more carbon rich.
So that's a level of detail we haven't gone into. So this is my one slide summary of our model for nucleosynthesis in the simulations. So we track 11 elements, including 9 metals that you see here, the most commonly measured ones. We have 3 channels for nucleosynthesis: core collapse supernova, 1A supernova, and stellar winds. And again, all of these abundances, for the purposes of our simulation, will be IMF averaged, because our star particles represent, IMF average stellar populations. So we're not going into that level of detail here. We're looking again at sort of elemental abundance patterns of, think elemental abundance patterns of a population of star clusters, for example. Okay, so This first plot shows the average, this is averaging across our simulation suite here, the average iron abundance as a function of stellar age in our simulations. So you can see and don't worry about differences between the isolated and the local groups here, they're relatively modest differences. So we see overall metal enrichment. So at early times, the progenitor was relatively more metal poor, and then it enriched over time. But with non-trivial scatter. So we have to be a little bit careful that we commonly conflate, say, metallicity with age. But of course, there's non-trivial scatter. So we should be a little bit careful about how quick we are to trivially relate, say, iron abundance to stellar age. So then you can think about, and without staring at this top panel too hard, if we measured the total scatter in metallicity across the disk, what would it look like? Would the total scatter in metallicity across the disk get bigger with time, get smaller with time, something more complex? So it turns out to have this really interesting history in basically all of our simulations, where, again, if we just take all stars forming across the entire disk and just look at what is the scatter in their iron abundance at a fixed time, it has this curious sort of U shape, where at really early times, the scatter is high, and then the scatter comes down and reaches a minimum about 7 gig years ago, and then increases again towards redshift 0. And as I'll show you in the next 2 slides, we can easily understand this interesting shape as a competition between just 2 processes, one of which is that there are significant azimuthal variations in the disk across time that are getting weaker as the disk settles. And as the disk settles and grows bigger, there's an increase in the contribution from increasing radial gradients. And so these act in opposite directions with time, leading to this interesting sort of U shape. So I'll just elaborate on that a little bit. So here's an image of star-forming gas in one of our simulations at redshift 0. This is just showing you the oxygen abundance. And you can sort of see hints of the spiral arm pattern, but mostly what you see is the strong radial gradient with relatively weak but noticeable azimuthal variations. And then as I go back in time, redshift 0.5, now you can see it looks a bit clumpier. The radial gradient is a little bit less well-defined. And as I go back to redshift 1, you're basically seeing that hole there, which is basically a cavity driven by a particularly strong burst near the center of this galaxy. The radial gradient is clearly no longer nearly as well-defined, and we see large azimuthal variations. So the typical history of one of these Milky Ways is at redshift 0, very strong radial gradient. It's the dominant source of inhomogeneity in these disks. But at early times, it's just the opposite. The radial gradient isn't very strong. Most of the variations are from the patchiness. If you want to think about it, they're azimuthal variations. So this just shows that. So this shows, I realize I missed the redshift label, but this is the basically iron abundance versus radius. This is at high redshift, it's basically flat. And then at redshift 0, you see a relatively strong radial gradient. And so this just quantifies it on the right. This is the strength of the radial gradient. So the change in abundance index per KPC as you go from the inner to the outer part of the disk. Don't worry about the different lines here. If you just look at basically the blue line here, that shows that at very early times, there basically was no radial gradient in most of these simulations. And then as the disks continue to settle, as the amount of turbulence that mixes the abundance radially tamps down, as the orbits become more rotationally supported and can sustain gradients from the inner and outer galaxy, we see this radial gradient become steeper and steeper. And if we then compare the strength of the change across the disk from the radial gradient from r equals 0 to the edge of the galaxy, that's orange here. So again, it's relatively weak at early times because there was no radial gradient, and it becomes stronger at late times. And compare that with the strength of the azimuthal variations that's in blue here. So this is basically, if you go around a circle, how much variation is there azimuthally? It's relatively weak at late times, but was a dominant source of inhomogeneity at early times. And we find that a typical transition between azimuthal dominated and radial dominated occurs somewhere around redshift 1, about 7 or 8 gig years ago.
Do the other, sorry, just do the other elements follow some similar things? There's measurements of the abundance gradient in H2 regions from, say, oxygen and nitrogen that show a flattening in the outer disks. It's controversial whether the gradient, there's a linear gradient. People solve for a radial gradient and then say, but all the outer galaxy points are a little high, as if there's a higher than you expect from the radial gradient. So it's like maybe they flatten out, which I think I saw in your iron, that it was sort of linear, and then as you went out, it started to not drop so fast.
Yes. So the answer to two questions is, one of which is most elements we've examined show these same qualitative trends, although the quantitative strengths can be a little bit different. And yes, in Matt's paper, we actually quantify this question in detail. We fit sort of two component, sort of a break to the profile. And we see as well that the abundance gradient gets, you can basically see it here up here, that the abundance gradient is steepest in the inner galaxy and relatively shallower in the outer galaxy. So it's not necessarily fit by a single power law.
Yeah, that caught my attention right there. So that's perfect. Thanks.
Yeah. And in Matt's paper, we try to understand where this comes from. I don't have time to discuss it now, but if you're interested, I'm happy to send you a draft. We think we have some insight, at least, as to where that break comes from. Okay, so I'll just summarize this part and then get to my conclusion, since I'm basically out of time here. So sort of a summary of metal enrichment over time and how it feeds into our how to even think about approaches to chemical tagging. As a Milky Way galaxy evolves across time, overall metallicity increases, right? That's as everyone expects. The radial gradient steepens. So at high redshift, there is very little radial gradient, again, because the turbulence in the ISM was quite high. Turbulence will drive mixing, especially in the radial direction. And so it's very difficult to sustain a radial gradient if your ISM is basically mixing on the whole scale of the galaxy. You just can't. Where it's important in high redshift is the azimuthal variations because of clumpy star formation and accretion rates. But then as the disk settles across time, accretion rates go down, the azimuthal variations reduce, although they don't go to zero. And the radial gradient becomes the dominant source of spatial variation, right? So there's a transition epoch about redshift 1 or so, where at least in these simulations, typically galaxies transition from azimuthally dominated to radial dominated. So what are the implications for this whole chemical tagging idea? Well, if you look at most papers on sort of weak or coarse grained chemical tagging, for the most part, people are using it to try to understand how stars may have formed at different radii and maybe have moved radially migrated to different radius, right? And I think that's a very interesting application, but I think we need to be a little bit careful that that's going to work well for recently formed stars. But if we start looking at stellar populations going back in time, the radial gradient wasn't the dominant source of inhomogeneity. Then we're really measuring, we think, azimuthal variations, which is a much more complicated regime to work in. So I think, especially for next generation surveys, people talk about measuring very high resolution spectra to get elemental abundances to less than 0.05 dex precision. I think we need to be a little bit careful about thinking, what are we trying to do here? And are we prepared to model complexities like azimuthal variations and clumpiness? Because that's basically, at the level of sort of precision of current elemental abundance measurements.
Sorry, just to stick in another comment. We didn't measure azimuthal abundances when we worked on this stuff, but we did measure that the scatter in the abundances in the outer galaxy were really much larger than you get from the observational error. So that's just another sort of measure of that problem.
And we have, in the Matt's papers, we have compared to, there's a handful of measurements. In the Milky Way, it's a little bit harder, but in nearby galaxies through resolved IFU surveys, there's also measurements of azimuthal variations that are comparable to the sorts of azimuthal variations at redshift 0 we're measuring here. So I think at least our predictions are in the right ballpark here. Yeah. All right, so let me just I'll have to skip the part on small scale structure for time. I just want to say two things before I finish. One of which is, if you're all interested, or just to be aware, that in order to make these simulations useful to the community, we have created synthetic Gaia surveys. So we put a test observer inside of one of these simulations and look at the simulation as if Gaia was observing it. So we have Gaia DR2 synthetic surveys we've created. And then also, this is work led by Robin Sanderson's group at University of Pennsylvania, and her student Farnag Nikitar has also now released synthetic SDSS apogee spectroscopic surveys. So now we can do apples to apples comparisons to these observations and then use these simulations as test beds if you want to ask how well will a given Milky Way survey be able to recover a given property of the Milky Way, for example. And then finally, I'm excited to share that as of last night, All of the simulations I showed you today are now fully publicly available. So I just led a public data release, and the archive paper is out today. You can go to this URL if this is at all interesting to you. We've released all of the Fire 2 simulations, full snapshots, including dark matter, gas, and star particles. So anyone can download them and play with them, and use them to test whatever is of interest to you. So I'll just finish here, and I tried to give you some sense of what we've been doing, of trying to connect our measurements of cosmology in the early universe that provide very firm initial conditions to the mass distribution that informs galaxy formation, and connect the dots all the way to today, where we're now at the level of creating realistic synthetic surveys of the Milky Way to compare with these Milky Way observations, and sort of give you an overview of some insight in the formation history of the Milky Way, approaches to chemical tagging. I ran out of time for GMCs and star clusters, but we also have released synthetic Milky Way surveys and public data for anyone to use. And I'll stop there if there's any other questions.
Thanks very much.
Yeah, thank you, Andrew. Other questions? Mike?
So just very briefly, I assume I guess it's your third bullet point. You must make some star clusters that look like globular clusters.
All right, you're going to force me to go back. So
yeah.
So I'll just very briefly. So this is work being led by Sarah Loebman's group at UC Merced now. So well, I'll just say briefly. So Sam Benincasa has been doing nice work looking at molecular clouds in these simulations. And on the right, you can just get a sense of comparison. This is the mass function of GMCs in these simulations. That's the colored lines compared with observations of the clouds in the Milky Way and M51. And then we're getting mass functions that are, sort of at least qualitatively comparable to what we measure in the Milky Way. So that's promising. And then we can look at the populations of star clusters forming within them. That's on the basically just giving a visualization of that in the bottom right. And so one thing we can look at is just the mass function of star clusters. So that's on the left. So DNDM versus the mass of the clusters. And we're getting sort of mass functions on the right that shows the slope of the mass function alpha. And then in the x-axis basically shows the mass range that the mass functions have been measured over. And the star there with the box is basically the mass function we're getting in fire. Now, we're not able to resolve typical star clusters here. These are very much the massive end of the star cluster population. You can see they basically sit near the boundary between open clusters and nearby globulars. So we're not yet at the point of getting down to like typical star clusters, but we are sort of getting, resolving massive star clusters and even up to globular-like things. Now, I'll just say, in case this is where you're going, it's one thing to resolve the formation of these star clusters, but because we're not doing proper collisional stellar dynamics, right? We're not resolving the internal structure of these things very well at all. They basically evaporate and mix, too fast. So we're not yet at this age of like being able to resolve the formation of globulars all the way, and there's their evolution all the way down to redshift 0. That's a much more challenging problem.
You could perhaps fudge it by tagging the things that you think might survive.
And yes, so like eMosaics has been doing this. I think it's a great approach. We're talking about it. We're thinking about it. It's on our radar. I think that's a very nice approach, and we probably will push on that in the near future.
Thanks. Nayesh?
So thank you very much for the very nice talk. So I guess one question is, which is kind of, I guess is very basic, is so you have this very detailed simulation. How can I build confidence that this is a correct picture? I mean, is there some test that it's non-trivial that it predicts this thing and I go and see that it actually matches within 1 sigma or within 2 sigma? I mean, we do that for cosmology, and you were talking about precision cosmology, right? So what is the analog of that, like fitting the CMB power spectrum, going through the Biggles and such? So what is the analog of that here?
Yeah, so I don't think there's a single analog. I mean, I think you're looking at one here, right? So if we want to have some confidence we can resolve star cluster formation, we should look at the properties of star clusters. So I think for galaxies, you want to look at a bunch of properties, and we've written 20, 30 papers now looking at, rotation curves, galaxy sizes, thick and thin disk fractions, you know, there's not a single thing. It's not quite, there's not necessarily a nice summary statistic like with the CMB. I think it's a multitude of things. Some things are holding up very nicely. Some things I think we see tension regarding. So, for example, most of these simulations have pretty big bulges, maybe too big compared to most nearby disk galaxies. The simulations I showed you today we haven't yet modeled AGN, so maybe that's a problem. So it's hard to give sort of a succinct answer to your question. Basically, you know, I think you need to identify the aspect of the galaxy that you're interested in and test it against it. I guess I can also say one other thing, which is, you know, our goal here is to understand the Milky Way is a system that we can measure best. So that's what makes it interesting, right? It's just one galaxy though, and that's what makes it hard, is how to generalize these exquisitely precise measurements of the Milky Way to a general statement about galaxy formation. And I'll admit that's, I think, one of the challenges with these cosmological simulations is while we do get the full nonlinear cosmological formation histories, we're never going to get a very exact Milky Way analog emerging, right? If that's what you're interested in, you know, there's a whole other approach, which is to design an idealized disk that exactly matches what you want for the Milky Way. The challenge there is it's hard to do that cosmologically. So there's sort of a back and forth here of, you know, we try to run as many of these simulations as we can to sample representative formation histories under the hope and expectation that we can bracket the formation history aspects of the Milky Way with enough simulations. But I can't tell you that here's our one gold standard simulation that exactly matches a bunch of observables of the Milky Way. It's, you know, in that sense, it's a much more probabilistic statement of, does the range of properties we observe match the Milky Way? And then also, there's tremendously valuable information from nearby galaxy surveys of, you know, measuring resolved populations in nearby galaxies like Andromeda, for example. So that's tremendously useful as well. So it's a bit more complex than just a single.
But just to follow up on that, I mean, I guess one analog I can think of is like a stellar mass function of galaxies, for example. But then for that, you need a lot of galaxies. And
So we, you know, you can do the next best thing, which is this semi-empirically constrained stellar mass halo mass relation. And, you know, in our papers, we have made plots of this for our simulations. And broadly speaking, from our Milky Way mass down to our faint dwarf galaxy mass, our simulations broadly agree with those M-star and halo relations. There's maybe like 1 sigma tensions here and there. And then a whole other talk I could give is, you know, these simulations also all have populations of satellite dwarf galaxies around them at redshift 0. You know, missing satellites has been a long-standing tension. I could show you plots of it, but basically the luminosity function of the satellites that we can resolve here agrees with what we measure in the Milky Way and M31. So that's another sort of figure of merit that seems to be, broadly speaking, in agreement with observations.
Great, thank you.
Yeah.
Okay, thank you, Andrew. I think we're out of time now, so let me just thank you again for coming and joining us today.
Thanks for inviting me. It was a pleasure.
Yeah, no, thanks for doing a great talk. Okay, bye everyone.